Hello and welcome to this video. In this video we are going to look at the properties of radiation. So if we now think back to particle physics, we looked at interactions that can happen between particles. We looked at things like annihilation, we looked at pair production, but these things we're not really going to consider anymore because what we're going to focus on in nuclear physics is just nuclear interactions. So we have to think back to particle physics and say, okay, what interactions did we look at that actually involved the nucleus of an atom? And those come back to be alpha decay, beta plus and beta minus decay, gamma decay, and electron capture. These were the five kind of nuclear interactions that we had back in particle physics, and we're going to revisit them now. Now, we should already know back from GCSE about alpha decay, beta decay, and gamma decay. And so what we're going to say now is I'm not going to recap the process of these things. If you do need a little bit of recap, I recommend you go back to the particle physics section of this course and have a look at the videos explaining the particle interactions. And they will explain the processes of alpha decay and beta decay. And we should know that after alpha decay and beta decay, you'll end up with some excited energy of the atom. Since it's just emitted a particle, it will have some energy left over, and so it emits that excess energy as a gamma ray. This is why we get gamma radiation as well. And so I'm not going to recap too much about those processes, but we are going to look at the particles that come out of those processes. And we know that those particles are alpha particles, beta particles, and gamma rays. And what we need to know about these particles are their properties. Okay, so we need to do some revision because most of these properties you will have seen at GCSE, and this will just be repetition to begin with. And then we're going to look in more detail as to how we actually came to these conclusions. How do we know that these particles have these kind of properties? So the first thing we need to look at are the particles. Particles of radiation, and now, as we've just said, they are alpha, beta, and gamma. The properties that we need to know first of all the constituents. So what exactly is an alpha particle, what exactly is a beta particle, what exactly is a gamma particle. We need to know the range of these things. So how far can this radiation actually go while it's still affecting things? We need to know what this radiation is stopped by. So how can we prevent this radiation from being harmful? And we also need to know the ionizing ability of this radiation. So can this radiation cause harm by ionization? Since most things that are harmful about radiation are based on the fact that they can mutate genes, but we'll look at this in a later video. So we'll go through alpha first, then we'll look at beta, and then we'll look at gamma. So alpha constituents, we should already know that it is a helium nucleus. So it is a helium nucleus, which is simply 2 protons and 2 neutrons. We know the range of alpha is not that big, so actually alpha can only travel for a few centimeters, and that is, so the maximum you'll probably get an alpha particle to travel after it's been emitted is going to be about 10 centimeters, but you'll find that all of the alpha particles emitted by the same source will always have an exact range. So all alpha particles will have the same range from the same source. Alpha particles have the least amount of energy because they are the biggest, so when they get emitted, they use up most of the energy to actually be emitted, and they end up with the smallest amount of kinetic energy, or the smallest velocity because they have the highest mass. And they are stopped by paper. So you can just put a thin sheet of paper in front of an alpha source and you're completely safe from that then. And the ionizing ability of these, it has 2 protons, which means it has a +2 charge, which means it's very ionizing, and it can pull electrons off. So this is a highly ionizing type of radiation. Okay, it is very dangerous. Now, the danger of this is kind of counteracted by the fact that it can't travel through skin, and the only way it can be dangerous is if it's ingested. Every teacher talks about this kind of Russian spy who got poisoned with an alpha source put in his food. And the reason these are so highly ionizing in comparison is because actually, if I were to say that alpha particle is just going to be, let's just have, this is my alpha particle with a 2+ overall charge. If I then had an atom here that had some electron in a shell, in order for this to actually pull the electron off, it just has to fly next to it, because if this is negative, it's already going to get pulled up by the electric force. So it's already going to be able to be pulled off just from the alpha particle flying past the molecule. It doesn't have to collide with it or anything like that. So it ends up being pretty highly ionizing. Now, beta particles, we do have 2 beta particles, so we obviously know that we have beta minus and beta plus. We also know that those are just antiparticles of each other, so the constituents are an electron, or a positron if it was the opposite. So if we were just going to look at beta plus, it would be a positron. The range on beta is a little bit longer because they have a smaller mass. They can travel for further, so they have a range of about 1 meter. So I'm going to say a few meters because it does depend on how much energy the beta particle is emitted with, and these, because they have higher energy, are stopped by thin aluminium. So it requires more more of a stronger material to try and stop this beta particle from passing through, and these are moderately ionizing. Now, compared to the alpha particles, we say they're moderately ionizing because for them to be able to ionize this electron in this energy level, this beta particle has to actually collide with this electron. Even if it was positively charged, it would have to get very close to it, much closer than a 2+ charge, because as we know from Coulomb's law now, we can say that the force is 1/4 pi epsilon naught q1 q2 over r squared. So for the same distance, we're going to have basically a square factor of the, or 2 times the amount of force that we have, and therefore we have a much more ionizing type of radiation. And the last type of radiation we have is gamma rays. Now, a gamma particle is just a photon with a frequency in the gamma region of the electromagnetic spectrum. Because this is a photon, this is light, it has an infinite range, so you can actually say that these gamma rays will go on forever. There is currently gamma rays hitting you that could have been emitted from a particle interaction that happened a million light years away in a different part of the universe. Gamma rays, because they have much higher energy, they can be stopped by thick lead. Now, some people would say that thin and thick are kind of subjective terms, so you can't actually define it as being thin or being thick. So how would we put some values on the difference between these? Well, thin aluminium is about 0.5 centimeters, so it's about half a centimeter, a few millimeters would be thin aluminium, whereas thick lead, we're looking at about 10 centimeters worth of lead to completely stop it. If we have anything smaller than that, it's not going to stop the, or it has a smaller chance of stopping the gamma rays from passing through, but it does reduce the intensity. And we'll look a bit more about how the intensity of gamma rays change in the latter part of this video. Now, gamma rays, their ionizing ability is weakly ionizing, because in order to ionize the same electron in that atom, it has to be absorbed by that electron. And because these are gamma photons, we can assume that they're probably going to have high enough ionization energy, as long as the molecule isn't like huge. And so these are the properties that we have of these types of radiation. You should be fairly familiar with all of this kind of stuff from particle physics AS, or even back from GCSE. You would have encountered all of these properties. Now from this point, we need to then ask, how do we actually detect these kind of particles? How do we know that radiation is being emitted in the first place? How do we know that there are different types? Like, what can we actually do to distinguish the difference between these? Is there any way we could actually separate them? Because what we actually find, and we'll look at this more in the theory of radioactive decay, but when something is radioactive, it will tend to emit all three types of radiation. Okay, and we'll look a bit more about why that happens, but it will end up emitting all three. So how do we know which type of radiation we're actually detecting? Well, the first thing we can do is play a little bit on the charges of these things. We know that the alpha particle has a 2+ charge. We know that the electron has a -1 or a +1 charge. For this, I'm now going to assume for the rest of this video that I'm just talking about beta minus, since it's much more common for that type of radiation to occur. And we know gamma is light, and light does not have a charge. And so we can say that if we have three things that are charged, we can put them in either an electric field or a magnetic field. What we tend to do is put them in a magnetic field, and that is then going to enable us to split the difference between these, because we know that if I was, for example, going to have a uniform magnetic field, and if you haven't checked out the magnetic fields videos yet, I would recommend watching magnetic fields before you come on to nuclear physics. This is a uniform magnetic field, and I have an emitter here that is emitting all three of these types of radiation. Now, if I have alpha decay, I'm going to change colors for this alpha decay. So if I change color, and let's have red as alpha, so let me just signify that here, red is alpha, then in order for the alpha particles to come in, so they're going to come in here with the same velocity. Since we know that these alpha particles are positively charged and they're entering this uniform magnetic field, they're going to feel a force. You can use your Fleming's left-hand rule here to then prove that when it feels that force, it will undergo a circular motion with this kind of radius here. Then we need to switch colors again and say, what happens if a beta particle comes into this magnetic field? Well, if it comes along the same trajectory with the same, well, we're assuming they have the same velocity. Obviously, when it happens in reality, the beta particle will have a much higher velocity than the alpha particle because of the range of it. And we know that if it's then negative, then our current is currently traveling in the opposite direction, which means actually our force is going to be in the opposite direction. So we end up with a force coming down like this. So we have an alpha particle will go in one direction, and the beta particle will come around in the other direction. Then the final thing we can look at is the gamma particle. And we know gamma is not charged, so hence you're not going to have a force present on the gamma particle, so it will just travel straight through. And this is how we can separate the three. We know that we have some positive charge, we have some negative charge, and we have neutral charge, so we can then look at the paths in a magnetic field to be able to decipher which one is positive, which one is negative, and which one has no charge. And this is how we can separate them. Now we've also, if I go back to my original pen, we already know this kind of equation here, that I can relate the magnetic force to the centripetal force that is felt by each of these charged particles. So just the alpha and the beta, because obviously the gamma isn't going to feel a force. And I could actually come up then with an expression for the radius of each of these, and then I could prove that actually, even if I had a beta plus here, I could distinguish the difference between the beta plus and the alpha particle based on the radius. If I cancel out a velocity on both sides, and I say the radius is therefore mv over bq, then I know it's not only dependent on the magnetic field strength and the charge, it's also dependent on the mass and the velocity, and I know all of those are going to be different, so I'm going to end up with two different radii. So this is the first way that we can actually distinguish between these types of radiation. How do we actually visualize this though? How could we actually tell? How do we observe the paths of these radiation? Because obviously they're way too small for us to actually detect. And so we have another type of detector called a cloud chamber. Now a cloud chamber uses a different kind of property of the radiation. The cloud chamber uses the fact that all of these types have a specific kind of ionizing ability. Now, what we find when we structure a cloud chamber is we have what we call a saturated vapor. So we just have a chamber full of a saturated vapor that basically allows for ionization of the vapor inside this chamber. As soon as we have an emitter inside this chamber that emits these kind of radiation, they will ionize the vapor, and you'll be able to see the traces left behind as the particles move through. This allows us to not only trace where the particles are, but it also allows us to then distinguish between which particles are being emitted. And the way we can distinguish is because their paths are completely different. So if we say that the saturated vapor is ionized by alpha or beta radiation, we can first have a look at, if we were to just view this cloud chamber from above, and let's say that we have just alpha particles. Okay, so this is the path that alpha particles would take. Assuming the source is somewhere down here, alpha particles move in dead straight lines. Okay, so they just get emitted from the source, and the way you see them is straight lines, all the same length. Okay, so alpha particles just have straight lines, all of the same length. Now, why is that the case? Alpha particles are the most ionizing. They will have the strongest effect of ionization, causing a very strong glow, so you can see the path all the way as it travels, and all of the alpha particles emitted by the same species have the same range. This is why all of the lines are the same, and they're going to be emitted in all directions, and this then allows us to track alpha particles. If we were to then switch over and look at beta particles are not as ionizing, right? So actually what we see when we observe beta particles is more of a wispy kind of, we see small little changes that occur like this, and each of these small traces that we see in this cloud chamber represents a single beta particle ionizing this gas. Now, because it's moderately ionizing, we can't tell the path of this beta particle as much. This is also true because they're much smaller molecules. It means that actually, if we're trying to trace them, they're in a very saturated gas. They're getting collided, or they're colliding with all of these gas particles. They have a Brownian motion. They move with random motion. They don't have a specific path in this chamber. But we see short, and it's often described as wispy trace. So we get short, wispy traces that occur all over the place, and this is how we can then detect beta particles. So we now have two very different visuals of how we can actually observe these and how we can change them. But even if we were to do this, a cloud chamber is quite a big, expensive toolkit. How do we actually perform this in a lab? Because this is one of your required practicals to observe the kind of difference between these kinds of radiation. So the third way that we can observe radiation is with a Geiger counter. Now, I've mentioned Geiger counters briefly before, and a Geiger counter is simply a device that we use that absorbs radiation and provides a count rate. So a Geiger counter is a device which absorbs the radiation, and I should point out here this is all types of radiation. This isn't just going to be just absorbs alpha, just absorbs beta, or just gamma. It will absorb all three, and for each one that it absorbs, it will provide a count rate. Okay, so it provides a count. So it counts how many radioactive or radiation particles that it detects in a given time period. If you turn it on and you leave it for 10 minutes, it will tell you how many particles it detects in those 10 minutes. Now, Geiger counters are very useful, and you will use a Geiger counter in your required practical. However, there is kind of this idea that if it detects all three, then how do we distinguish between the types? And the only real way is to now look at their properties again and say, okay, we've already used the fact that they've got some charge to use the magnetic fields. We've used the fact that they are ionizing to look at these cloud chambers. What other kind of properties do they have? And one of the biggest properties is their range. Their range is very significant for each of them. So if we place the Geiger counter very close to this source and we start reading a lot more than we do if we place it away from the source, this means that we're going to get alpha decay emitted. If we place it right next to it, just a few centimeters away, we're going to get alpha emitted. If we then go to a meter away and we're still detecting something, we've probably got beta or gamma. If we then go 10 meters away and we have still got things being detected, that's definitely just gamma, because beta can't reach that far. So we change the range between the particles, or let's call it a source, and the detector. And this can then allow us to specify which type of radiation we're actually detecting. Now we need to look at the final kind of property of this type of radiation, which is the fact that gamma radiation has an infinite range. Now, this should surely mean that if we know that gamma radiation from GCSE, we know it's not exactly healthy for anyone, right? We know it can cause cancer. So if we then have an infinite range and we have loads of radioactive sources in the universe, not even just on Earth, so surely then everyone's getting constantly bombarded by infinite amounts of radiation, and then nobody's really safe. Why are we not all just developing cancer because of all the gamma radiation that's occurring? Now, the answer to this is the fact that the intensity of radiation is not going to be the same everywhere you stand. And this is known as the inverse square law. If you kind of does make logical sense to think about it. If you stand closer to the radioactive source, it's more dangerous than if you were to stand 3 miles away from a radioactive source. Now we just need to say, why is that the case? And the inverse square law, if we were to put it in a simple mathematical expression as it is given on your formula sheet, it's just that the intensity is proportional to 1 over the distance squared. Now, we've seen this kind of proportionality before. It was for the forces in gravitational fields and electric fields. And the same thing occurs here. When we have this inverse square law, it means that if I were to double the distance from the source, so actually, let me just say that in your formula sheet, this is written as I is k over r squared. And this k is just some sort of constant of proportionality. So this is just some constant that relates the two. It is not the Boltzmann constant. It is just some value that relates the intensity of that source of radiation to the distance. So what we can say from this is that if I were to, for example, have a source here. This is my gamma emitting source, and I have a distance, let's call it r here. I get this kind of, I have a spherical emission of all of these particles. There's never just a single direction that it will travel in. I will start to emit them in any direction. It's completely random, and especially with these gamma rays, they will be emitted in all directions. And so I have kind of this spherical emission that will travel around everywhere. Okay, it travels in all directions. If I were to just take one single slice of the surface of this circle here, so the radiation has now traveled this distance r to get to the surface. If I were to then double this distance and say that I'm actually going to go further, I'm going to have a bigger circle, and actually what we find is that I could fit in 4 of these smaller circles. Obviously my geometry isn't exactly perfect in this diagram, but if this was r also, I could fit 4 of the original area onto the new surface. Now that means that if I have a certain amount of gamma rays incident on this first surface, my intensity, it might be worth noting, intensity, if you wanted to put an equation on it, is just the amount of energy, or let's call it power, the power incident on a surface per unit area. Now, the power is the same because it's the same amount of energy that's being transferred, and it's all going to travel at the same velocity because it's all traveling at the speed of light. So the power is the same, but now the area is 4 times as big, which means actually I've decreased my intensity by a factor of 4 by doubling r. And this is really what the inverse square law is. It's if I double the distance, the intensity falls by a factor of 4. Okay, now obviously it's not only if I double it, obviously if I times the distance by 4, then I'm decreasing the intensity by a factor of 16, because that would be 4 squared, and so on. So it means that actually the further you are away from a gamma source, the safer you are, because even though you may have still be being hit by them, you're probably most definitely being hit by gamma rays right now, you're not going to absorb the same amount of energy. You don't have the same intensity acting on your body as you would if you were standing maybe 5 centimeters away from this source. So you still don't have to worry. This radiation is not dangerous from a distance because of this inverse square law. Okay, so now we've revised the properties of these types of radiation. We know that we can deflect them all in a magnetic field and tell the difference. We can observe them all in a cloud chamber, and we can use Geiger counters to actually count how many are being released. And we can also describe the intensity of gamma emission by this inverse square law and explain how the intensity is going to decrease by the square of the distance as you travel away. Thank you for watching.